Hi everybody, welcome to another video in Pre-Calculus, section 3.1, Polynomial Functions and Models. So in this section, it is just a review what we have in coarse algebra. So first, we define a polynomial. A polynomial function or a polynomial is given in this form. We have x to the n power, where n is the natural numbers. Right. We have x to the n minus 1 all the way to a constant a sub 0, and on the a sub n minus 1 to a naught, all of those are constant, called the coefficient of the polynomial. N is greater than 0 and integer, or we just say n is a natural number and x is variable. The first coefficient that is not equal to 0, that go with the highest degree of the polynomial, is called the leading coefficient. So a sub n here is the leading coefficient because that is the highest degree, and n is the degree of the polynomial. So it's just some terminology, and you should know this already. The domain of polynomial function is the set of all real numbers. So we have this. We don't have anything in under the denominator. We do not have anything inside the even root. So it is defined everywhere. The coefficient of real numbers, the leading term is the one with the highest degree, and the leading coefficient is the coefficient of that term. A naught is the constant term. The degree is the highest power of the polynomial. And if it is in the standard form, we write everything in the decreasing order of x. A constant function has degree of 0, and we do not assign a degree to 0. F x equal to 0. Right. First example, determine which of these are polynomial. So we, according to the definition, we cannot have the square root. So this is not a polynomial. And we cannot have anything at the denominator. So this is not a polynomial either. And this is a polynomial. We just have the x raised to a natural number. So all of this is good. Now this is not in the standard form. In the standard form, it is written as the decreasing power of x. So if it is state the degree, so degree is 4. And then define the leading term. Of course, leading term is 3x to the 4th, and the constant term is minus 5. Leading term, the one with the highest degree, and constant term. Yeah, this is not a polynomial. The graph of polynomial function is both smooth and continuous. By smooth, we mean like this, meaning there's no sharp turn. So this is not smooth, or there's a corner. This is also not smooth. Yeah. So we cannot have any of this. And also, it has to be continuous. And continuous, we mean we cannot have a gap, we cannot have a hole. So this is not continuous. So Pretty much think of the roller coaster. It cannot have any corner or sharp turn. It cannot have any gap or any hole. So this is a graph of the polynomial function, smooth and continuous. Most of this is just a review of coarse algebra. Right, power function. Power function is just one term of the polynomial. We write a to the x to the n, where a is a real constant, not equal to 0, of course, and n is greater than 0, n is an integer. Of course, we can put those together and we say n is a natural numbers. Right. Now, properties of the power function. Now we have x to the n. First, it is an even integers, and then we have x to the n for odd integers. Of course, if x to the n, if n is even, then it is an even function, and the graph is symmetric with respect to the y-axis. If n is odd, it is an odd function, and the graph is symmetric with respect to the origin. Right? So, the graph of an odd function is like this. I mean, one up, one down. It could be the other way around, but it should be like that. Even function, so it will be symmetric on the y-axis. The range, if it is just x to the n, the range will go from 0 to infinity. For x to the n, when n is odd, the range from negative infinity to infinity. And the graph will be steeper when x greater than 1 and x less than negative 1. Yeah, so yeah, when n increases, the bigger n, the steeper the graph is. So those two are the same, and those two are the same as well. So the higher the degree, the graph tends to be very flat near the 0. Right. So characteristic of an even function is that it is like a U. Could be an upside down U, but it is symmetric on the y-axis. X to the n to the odd degree is symmetric on the origin, meaning that if we have a pole that is y value is positive, there must be a pole across from it, from the origin. So that's why one of them is positive, one of them is negative. One goes to infinity, one goes to negative infinity. All right, now let's sketch the following graph: 2 minus x to the 5th. So this is like we did with the previous section. X to the 5th, it is an odd degree, so we can have something like this. So that is the basic graph of x to the 5th. Now what we have is the minus or the negative. The negative here. Yeah, let's just rewrite this as negative x to the 5th plus 2. Negative x to the 5th plus 2. So this negative here, we turn the graph upside down. This is vertical reflection. So this point, up is down and down is up. So this negative flip or reflect vertically. And then after that we go up 2 units. So yeah, we just get a sketch here. Next, let's sketch 2 times x plus 1 to the 4th. X to the 4th power is kind of like u. It's not a parabola for xy, but this is more of a u than a parabola. And I should say this is when x close to 0, it is extremely flat. So that is x to the 4th, the basic graph. We have 2 here, and then we have, I forgot what color code that I use, but +1 here. +1 here will be 1 unit to the left, and 2 here is the y values multiplied by 2. So we multiply y values by 2, and we would move inside the, we do the inside the parentheses first, and then outside. So we move 1 unit to the left, and then we multiply by 2, meaning the y values by 2. That means we want to make it stable. So whatever the y values is, we multiply by 2. Yeah. So 1 unit to the left, and then stretch it vertically. Now, more on polynomial or polynomial function, zeros and multiplicities. Recall that the function, if that is a function and r is the real number for which f of r equal to 0. So that is the definition of 0 of the function. A 0 of the function is whatever the values that make the function equal to 0. Yeah, that's what we have here. So if it's a real 0, actually it is just a 0, then the function at that value is equal to 0. And with that, yeah, real or not, it doesn't. It still applies if it is not real. Yeah. However, if it is real, so that we will have the x-intercept. That's the only thing. Yeah. I mean, the definition of 0, it could be it doesn't apply to real numbers. It applies to all the complex number as well, not just real numbers. It applies to complex numbers as well. But we put the real numbers here so we can have the x-intercept. That's all. Because yeah, the x-intercept must be real numbers. Right. So if r is the real 0, then of course r is the solution of the equation, and f of r equal to 0, and x minus r is a factor, and r is the 0 of the polynomial function. So all of this are equivalent. When we have 1, we have everything else. Right, and we have x minus r is a factor of f. So all of this we have. Right, I mean, if we have one of them, we have everything else. If a polynomial function is factored completely, it is easy to locate the x-intercept of the graph by solving the equation by zero product properties. Zero product properties meaning that if the product is 0, then one of them, at least one of them is 0. So A is 0 or B is 0. So that is the zero product property. So if we have the factors, if we have the function, the polynomial factor completely, then each at least one of the factor must be 0. Right, from there we can get the x-intercept, we get the 0. Like that, when we have one of this, we have everything else. Now, let's see how it works. Find polynomial of degree 4 whose zeros are -1, -2, 2, and 4. So we know that those are the zeros. I just let's write x equal to -1, x equal to 1, -2, x equal to 2, and x equal to 4. Now, if those are the zeros, then x minus those numbers will be factors. So we will get the factors. X will be minus those numbers. Will be a factor. X minus -2 is a factor. X minus 2 is a factor. And x minus 4 is a factor. If it is a number, x minus that number is a factor. Because of that, we can have a polynomial will be equal to, we just multiply all of this together because those are the factors, right? So x plus 1, x plus 2, x minus 2, and x minus 4. Now we can put a leading coefficient here, because if this is a constant equal to 0, this constant does not affect the 0 of the problem. So we might have the leading coefficient here and does not affect anything else. Yeah, so potentially we may have that. Now, the rest of this is, if we want to, we can multiply this out. But the question did not say that we have to multiply it out, so just leave it like this. Of course, if we multiply this out, it's put in the decreasing order of x, and we have the standard form. But yeah, just multiply it out. It's not that big of a deal. But this leading coefficient do not affect the zeros or the factors. Yeah, the leading coefficient here in this form does not affect the 0. Because it does not affect any of the factors. So that's why we just put the leading coefficient there. Right, like I said, we could multiply now, but yeah, let's not do that. So those are the zeros. Next, the multiplicity. If x minus r to the m is a factor of the polynomial, and x2 minus r to the m plus 1 is not a factor of f, then r is called the zero multiplicity. I mean 0 of multiplicity m of f of x. Then we say, why do we have the business of x minus r to the m and x minus r plus m plus 1? So think about an example. Let's look at an example like this. X minus 3 to the 4th power, x plus 1 square. Let's say we have that. And then of course we have x minus 3 is a factor, right? You can also say x minus 3 square is a factor, or x minus 3 cubed, or x minus 3 to the 4th, right? So we may have x minus 3 is a factor, x minus 3 square, x minus 3 cubed, and x minus 3 to the 4th, but not x minus 3 to the 5th. So we will take the one with the highest degree, and that gives us the multiplicity of that 0. Right, so that's why we define multiplicity that way. Right, now numerically, the sign of f of x does not change around r if m is even multiplicity. So we have an even multiplicity here. Yeah, even multiplicity. I just spelled out. Be this one. You see, it is negative. When it hits the 0, it will bounce back to negative. That's what we mean. if m is even, the sign do not change when we cross the 0, around 0. And the graph will touch the x-axis and then turns around. All orders are odd. It will go across the x-axis. So one of them is negative, one of them is positive. One of them is positive, one of them is negative. Right? So an even multiplicity, it hit the x-axis and turn around. Because of that, the sign will be the same, either both positive or both negative. And if it is an odd multiplicity like 1, 2, and 3, one of them is positive, one of them is negative. Right? And the graph near the zeros of odd multiplicity, the graph will cross the x-axis. Right. One more thing that we haven't mentioned about this is those are the zeros, all right. But if we have the high multiplicity, let's say this is an x-axis, even though when it crosses, it could be like this. Yeah, all of this will go straight through it. It tends to be flat. So when the multiplicity is greater than or equal to 2, whether it touches or crosses the x-axis, it doesn't matter. It will be flat at the zeros. I mean, flat is the relative term. Flat at the zeros if multiplicity is greater than or equal to 2. If it is 1, it will go through it. If it is with the bigger multiplicity, it will be flat. So it could be like that. Or it could be like this too. Yeah, so at those 0, it will be flat if the multiplicity is greater than or equal to 2. Right. Here's some example. Find the zeros and multiplicities and the behavior near the x-axis of the following function. So we have 3 things. Zeros, multiplicity, and the behavior near the x-axis. Okay. Yeah, find the ruler. So what we have is zeros, multiplicity, and then behavior near the x-axis. Or we could say behavior near the 0. Right, first, so we look at the polynomial. Luckily, this is factor completely, so we just let every factor equal to 0. First of all, 7x cubed equal to 0. Yeah, so x equal to 0. So if we have the factor of 7x cubed, and we make that equal to 0, then of course the 0 is x equal to 0. There's the power of 3, so that is the multiplicity of 3. And if it is odd multiplicity, it crosses the x-axis. So that is the first. Zeros and the multiplicity. Yeah, the 7x cubed we can rewrite as 7x minus 3, x minus 0 cube. Yeah, so in that case, 0 is a 0. Right. Next, we can let the factor x plus 1. If that factor equal to 0, then the 0 is negative 1. The power the multiplicity here. By default, it is to the first power, meaning multiplicity is 1. And if it is odd, 1 again, we crosses. The graph crosses the x-axis. If it's odd. Next, we have the factor x minus 1/2 square. If that is equal to 0, then we have x equal to 1/2. Multiplicity of 2, which is the power of that factor. And if it's an even multiplicity, it will touch the x-axis and turns around. Yeah, so simple enough. Same thing for the next example. If it is factored completely, it makes things easier. If it's not factored, then yeah, that might be a problem. If it is not factored, then we have to factor, of course. Zeros, multiplicity, let's put that in plurals. And behavior near the x-axis or near the zeros. Right, we have the x minus 3. Make that equal to 0, so we have x equal to 3. And by default, this is multiplicity of 1, which means it crosses. The graph crosses the x-axis. If it is odd. And then we have x plus 2 to the 4th. And we make that equal to 0, so meaning x equal to -2. And the multiplicity, this is multiplicity of 4. So if it is an even number, it will touches the x-axis and turns around. Now more on the graphs, polynomial. A graph of polynomial of degree n, we have at most n minus 1 turning points. In other words, if a graph has n minus 1 turning point, then the degree is at least n. Now the n behavior. For very large values of x, either positive or negative, the graph of the polynomial function resembling the graph of the highest power term. So what it means is only the one with the highest power term matters at x get very large or very small. So let me write this. As x goes to infinity or negative infinity, only the highest power term matters. I'm not saying the leading term, because sometimes it is not in the standard form. Whatever with the highest power matters. Where that is. Yeah. We might have something like this. where the highest power term is not leading the polynomial. Of course, it must be it's not in the standard form either. So as x goes to plus or minus infinity, only the highest power term matters. Now, we keep that in mind. Only the highest power term matters. Once again, the just highest power terms matters. Yeah, just okay. Like that. All right. Now, with that, when x is in that case, that behavior will be just like the one with the highest power. So meaning that if degree is even, so let's continue this note, important note. If degree is even, we have x to the n, which is even. So it's going to be, it doesn't matter, x to the n. When degree is even, we will have, because it is symmetric on the y-axis, so we have the same behavior on both ends. And as x goes to infinity, and then as x goes to infinity, meaning the right end, if x goes to positive infinity, meaning it's positive, x to the n power of course go to infinity as well, meaning that the right ends go up. Yeah, maybe I just draw the picture. This is explain. Yeah, just go up. Let's just look at some example here. Determine the numbers of turning points and the end behaviors of the following function. All right, first we look at the degrees. Degree of this is 3. If it is 3, the number of turning points will be at most 3. 3 minus 1 will be 2. Number of turning points will be, it's not exactly 3 minus 1, but it is at most, we say at most 2. Yeah, will be 1 less than the degree. By the way, we need to look at the highest power term, which is this. We say negative 2 x cubed. So this is the right end go up. If we have x to the n, of course, go up. Right? Now, the highest power term is negative x cubed. So the right end is not always up, but the right end here will be as x goes to infinity, if x go to infinity, if we put positive numbers in here, that's going to be negative, right? We say negative 2x cubed. When x go to infinity, that will goes to negative infinity, right? Yeah, if we put the positive numbers there, it's going to be negative. And if it's negative, meaning it falls, meaning it's going down. Now, the degree is odd. If degree is odd, meaning we will have the opposite behaviors. Yeah, degree is even, same behavior. If degree is odd, it's opposite behavior. So I should say degree is even, same behavior. Degree is odd, yeah, only write one of them. Degree is odd, we have the opposite behavior. And here's some example. So because degree is odd here, so we have the opposite behavior. Meaning that if the right end go down, we just draw an arrow, go down, that means the left end opposite to that will go up. So we have the end behavior, the right end go down, the left end go up. Yeah, so we don't have to memorize anything. We just look at the highest degree term, highest power term, and then we can determine the number of turning points and the end behavior. Sorry, I paused the video and I forgot to hit play again. So the highest power term is going to be that negative 5x to the fourth power. And with that, the degree is 4, and the number of turning point is 1 less than that, 4 minus 1. Now, it is much better to determine the end behavior by just see where it goes to infinity or negative infinity. When x goes to infinity, negative 5x to the fourth goes to negative infinity, so the right end goes down. The left end, where we will let x go to negative infinity, and that when x go to negative infinity raised to an even, it's going to be even with an extra minus, that makes it negative infinity. So we said the left end goes down. Sorry about that. I paused the video to change the ink, and I forgot to hit play again. Right, now this one is a little more difficult. We try to get the one with the highest power terms. So if it is the highest power terms, let me start again. If it is the highest power terms, where we have minus 3 and plus 2, it doesn't matter because the x has the higher power than the 3 and the x has a higher power than the 2. So whether we have those numbers or not, it doesn't matter. We just take the one with the highest power. That gives us x to the 8. An example to that is if we have something as x squared plus 3x minus 2 cubed, for example. If we want to find the highest power terms, we can just ignore those that are not highest power. Yes, we just multiply all of them out. That gives us the highest power terms. So we do the same thing here. Ignore that, and we have the one with the highest power term. Right. Now, if it is to the power of 8, because that is the degree, and the number of turning points will be at most that number minus 1. So 8 minus 1 is 7. So we have at most 7 turning points. Next, the right end, the end behavior. The right end, for that highest power terms, when x go to infinity, x to the 8 go to infinity, so the right end go up. When the left end, when x goes to negative infinity, x to the 8 goes to negative infinity. Right, it is to an even power, right? So where x is negative, it's still positive, so still go to infinity. So the left end go up. So the end behavior we will use when x go to infinity or x go to negative infinity to determine that. Right. Now, to graph a polynomial function, we actually have to go through all of this. But what we focus on here, those are this will be the characteristic of polynomials. Of course, all the down is smooth and continuous, and on the turning points. But we will, based on the graph, we just focus on this part. So find the zero, multiplicity, and the end behavior. We're going to use that to sketch the following graphs. Right. So two things: zeros, multiplicities, and behavior near the x-axis. So 1, zeros, multiplicity, and behaviors. Near the x-axis. Yeah. Right, zeros, multiplicity, and then behavior near the zeros or near the x-axis. Right, so first we have the factor of 2x squared. Make that equal to 0. We have x equal to 0. Multiplicity will be 2, that power 2, and because of that it will touches the x-axis and turn around. That's the first one. Next we have the factor of x minus 2 cubed. If we make that equal to 0, we will have x equal to 2. And multiplicity of 3. And if it is an odd number, it crosses the x-axis. Yeah. So we do exactly like what we have here. Exactly what we have here. Next we have x plus 3. We're going to make that equal to 0, so we have x equal to negative 3. multiplicity, there's no power here, so this is 1. And if it is odd, it will cross the x-axis. So that is the zeros, multiplicity, and behavior near the x-axis. Second, we'll go to n behaviors. So for that, we find the highest power or the highest degree terms. Yeah, we will take the highest terms. So ignore the 2 because that doesn't have the power compared to x, so we just take the one with the highest power. So multiply all of that, we have 2x squared times x cubed times x, so that gives us 2x to the 2 plus 3 plus 1, 6. That is 2x to the 6. Now the n behavior. As x goes to infinity, that means the right end 2x to the 6 goes to infinity as well. Because it's even, put it there, it's going to be even. Meaning that the right end go up. Now, as x goes to negative infinity, 2x to the 6 is still positive infinity, because an even power, negative in an even power still turns to positive. So we have the left end go up as well. And of course we can say the number of turning points will be at most 5. Right. Now put all of this together and we should have the graph. So first the graph will be at 0, 2, and negative 3. So we have those zeros, 2, and negative 3. Now the end behavior, the right end is up, the left end is also up, right? Yeah, because we have that is the highest power term, right? So the right end is up, the left end is also up. At 0, it will touch the x-axis and turn around. At 1, it will cross the x-axis. At 3, it will cross the x-axis. However, because of this of the high order higher than 2, so those two, the graph will be a little flat. So when degree is greater than or equal to 2, the graph tend to be a little flat there. So let's go. On the right end it is up, so it will be up, and when it hit the 2, it will be flat at the 2, so it will be like this. At the 2, it will be flat. It's flat, but it will go through it. Now with that, of course, it have to go up and hit this point again, right? But when it hit the 0, it will touch the x-axis and turn around. So we'll come back, touches the x-axis and turn around. Of course, I could do, yeah. Using this, we won't be able to know how low this graph goes, but at least we know that. Now, if we go up, eventually have to. If we go down, eventually it have to go up and hit the negative 3. When it hit the negative 3, it will go through it, not flat, but go through it. And then on the left end, it will be go up. So I have the graph look like that. Yeah. So a little flat here and here. So let's see if it actually like that. 2x squared x minus 2 cube x plus 3 yeah, just go straight to negative 3. I have to zoom out or change the windows. The x is okay though. Let's just go from negative 5 to 5. That would be better. Hit Windows and change to that. The y values, let's change to something big because we need the end behavior. So negative 1000 to 1000. Every scale is going to be 100 for each tick. Yeah. We won't be able to see this part here because that is too small. It's go here and then go back up. If we want to look at that closely, yeah, we won't see the lowest point here, but we see the dip. We see a dip here. Right, that's what we have. Right. The graph will focus on those things only. Now, let's look at this. So, of course, for the zeros, we don't really need to do that, but for later on, for the end behavior, we need that. So we still have the highest power term, still need to write that out. The highest power term. Negative x minus 2 square x plus 3 x plus 1 cube. So we ignore the 2, the 3, and the 1. Just take the 1 with the highest power. So what do we have here? 2, 1, and 3. So that is 6. And so negative x to the 6. Sorry. Yeah, that's to the 6th power. Right. First, the zeros, multiplicity, and the behavior near the x-axis. So that's what we do first. Right, so we have zeros, multiplicity, and the behavior near the zeros or near the x-axis. Right, that's x, negative x to the 6. Right. First, the negative doesn't do anything to the zeros. We have x minus 2 square. And because that gives us x equal to 2, multiplicity of 2. And that, of course, if it is even, that will cross the x-axis. I mean, touch the x-axis and turn around. And then next we have the factor of x plus 3. Make that equal to 0. So if x equal to negative 3, multiplicity of 1, and that will cross this. It will cross the x-axis. and then the factor of x plus 1 cube. Make that equal to 0, we have x equal to -1. And multiplicity of 3, because that also out, so we'll cross the x, crosses the x-axis. Next, we have the end behaviors. Right, the right end is where x goes to infinity. So as x goes to infinity, that highest power terms. If x is positive, this will be negative. So the right end goes down. Now x goes to negative infinity. Put in there, that's still negative. So the left end also goes down. Because the number of turning point will be 1 less than 6, will be at most 5. Right, now put all of this together. Before we do that, multiplicity of 2 and 3, so those will tend to be flat. We have 0 at 2, -1, and -3. Yeah, so the right end go down, so it go down here as it go to the right. But at 2, it's going to touch the x-axis and turn around, so we're going to have it like this. Touch the x-axis and turn around. Now, if we go down, eventually you have to go up and hit the -1. When it hit the -1, it will be flat, but it will go through it. So yeah, it's flat. And then you have to go down to hit the -3, and it will go through it. Because this is the multiplicity of 1, it will cross. It will cross and go through it, not flat. Right, let's try to see the graph real quick. Minus x minus 2 square x plus 3 x plus 1 cube. And then we see the graph. Even it hit the 2, but it didn't even show. So let's zoom. Let's change the windows. Yeah. So as you see, it will go down on the left, down on the right, and hit the -3. And then when it hit the -1, it will be flat, but it will go through it. And then when it hit the 2, it bounces and goes down. Right, so that's what we have. Right, more examples. Which of the following graphs can be a graph of polynomial? So, the graph of polynomial, smooth and continuous, two things, right? So, when we see this, that is not smooth. So it's not a polynomial. There's the gap here, so it's not continuous. So this is the only graph that is a polynomial, because that is both smooth and continuous. Right. For those that could, so this is the graph that could be the graph of polynomial, so potentially a polynomial here. state the degree. So what is the degree here? So we have up and down and up. So 1, 2, 2 turning points. So the degree have to be at least one more than that. The number of turning points is one less than the degree. So the degree is one more than the number of turning points. I mean, at least. Have to be at least one more than that. And then the zeros, of course. X equal to 2, x equal to 0, x equal to -2, x equal to 0, and x equal to 2. Those are the zeros. So it's easy to determine. But if it's not smooth, it cannot be the graph of a polynomial. If it's not continuous, it cannot be the graph of a polynomial. Now, take everything we know, and we even have the graph that doesn't have any x or any numbers on the x or the y-axis. Can we determine which of the following graph can be of this function? So, what can we deduce from here? First of all, the highest degree term is x to the 5th. So in that case, so we say as x goes to infinity, x to the 5th goes to infinity as well. So the right end goes up. On the left end, be as x goes to negative infinity, x to the 5th will go to negative infinity. So the left end goes down. Right, so we need the graph that's the left side go down and the right side go up. So it cannot be this one, right? Because of this behavior, the right side is up, the left side is down, so it cannot be this one. Right, what else can we have? Number of turning points. So degree is 5. So how many number of turning points we can have? Will be at most that number minus 1. So at most 4. So let's see. So let's see 1, 2, 3, 4. That's good. 1, 2, 3, 4. That's okay there. 1, 2, 3, 4, 5, 6, 7, 8. So this will have too many turning points. Will not work. So without the 2. So which one do we determine? Right. Now one thing we haven't done on the graph is this. Now if we let all the x equal to zeros, f of 0, so that go to 0, that go to 0, that go to 0, and that equal to 3. Right? Now, when we put 0 for x, the function equal to 3, and that is positive. So it has to be this point, right? And it cannot be, so the y-intercept cannot be that point. So because of that, this is the potential graph of that function. So, yeah, we don't even need to know what is A, what is B, but the graph will look like that. Yeah. So this, I will take a lot of things that we learn in this section, put together, and we can deduce that this is the graph of that function, including the y-intercept. Of course, we use the x-intercept. We cannot use the x-intercept here because we have to solve for it, and we can't because we have A and B. Right. So the end behavior, rule that one out. Too many turning points, rule that one out. The y-intercept, that has to be this. Right. Next, write polynomial function whose graph is shown as the follow. Use the smallest possible degree. So when we look at this, we see that the x-intercept those. The x-intercept is same as the zeros. So first we have the x-intercept, all the zeros, -1, 1, and 2. Right, let's say x equal to 2. So those are the zeros. Now the multiplicities, sorry, the factors. If those are the zeros, then the factors are x minus those number. One factor, x minus 1, one more factor, and x minus 2. Yeah, we put all of that together, right? Right, what else do we have? So this looks like it will go through it, and touch the x-axis and turn around. So based on the graph here, this is multiplicity of 2. Because it touched the x-axis and turn around. It could be 4 or 6 or 8, but yeah, we choose the one with the smallest degree, so that could be 2. And those are we go through it and it's not flat, so this one we can say that definitely this is multiplicity of 1. Be at those 2 points. So because of that, we put all together. We have this factor of x minus 1 or x plus 1. I will have the factor of x minus 1, a factor of x minus 2. And furthermore, we have the multiplicity of 2 at -1. So this we should have a 2 there, because of that multiplicity of this factor, x minus 1. And then we might have the leading coefficient. Yeah. Now one thing we haven't used of course is this point right here. Meaning that this will equal to 64 when we put 3 in for x. So I have 64 that's 4 square. 4 times 4 is 16. 3 minus 1 is 2. 3 minus 2 is 1. So 64 equal to 32 a sub n. So a sub n will be equal to 64 divided by 32, so it's 2. So the function that we will have is a sub n is 2, x plus 1 square, x minus 1, x minus 2. Right. And we, of course, we choose the one with the smallest possible degree. Yeah, we can make this to the 4th power, but like I said, we want the one with the lowest degree. Right. Next, it's just a polynomial regression. It's just an application where we use the calculator. So this, we found the best fit line if it is a linear function, or the best fit polynomial if it is quadratic, cubic, or any higher degree. So let's say what we have is a table of numbers like this, because we can plot those points and then we can find the line that best fit them. So just get so we can get used to it. If it's that, then enter. I think we just hit start without hitting the enter, so we don't really need to enter. Okay, hit start, and then under edit we hit enter, so we can enter the list here. Usually if there's some numbers in there, just clear by highlight the list, hit clear, don't hit delete. Just hit clear and enter. Clear and enter. Highlight the list, clear and enter. If you accidentally hit delete, it will delete the list completely. In that case, you have to delete all of them. And then just enter this name again, L1. So hit second, number 2 for L2. So we name it again. If you actually delete them, have to name it again. Now, in this case, let's just put those numbers here. -3. Use this negative, not to subtract. -2, 0. Sorry. 2, 3, and 4. -1, -1, 4, 8, 9, and 14. Right, so enter those numbers in. Now if we want to plot them, let's see how it looks like. Just second mode to quick. Now to plot, we have to turn in the stat plot. Second stat plot. Highlight the 1, hit enter, and turn it on. Just leave this first one so we have plot in the pool. X is from the list 1, Y from list 2. So that's good there. Just hit enter and then hit graph. So we have those pool. Let's change the coordinates so we have to cover all of this point. Hit the windows from -5. That's okay. Up to 4. Yeah, to 5. That's good. Yes, -5 to 5. Okay there. The y values will go from the lowest -1, the highest 14. So let's say the lowest y values is -2 and the highest is 15. And we divide for every 2. Right. Every 1. Why not? And hit graph. So we have those points. Sorry, I should turn off the function. Yeah, clear the function. Right, so we have those points. Now we're trying to draw the line that best fit this. So remember, hit stat and edit. We have those lists. Now if we want to get the best fit line or best fit equation, what we do is hit stat again, go to the second tab, and we will use the linear regression. List 1, list 2, and we just calculate. It will give us this equation, so we will write out for the linear function y equal to 1.8983x plus 4.5678. Right, so we found the function. Now if we just graph that function, it could be good. However, even better, hit stat, calculate linear regression. We do all of that, but store the regression equation. Here we hit alpha, not alpha, sorry, variables, y variable, function y1. So we store that into y1, and we calculate. We have the equation. Now when we hit y, the y1 is the equation that we have. Now if we graph it, you see we have those points, and this line is the best fit line that goes through. So the distance to all those points will be, this is the best line that will be closest to all the points. Right? Now we can do the same thing. Stat, go to second tab, and we go to quadratic regression. Still calculate the same thing, but this time let's say we store the variable into function y2 and then calculate. We will have the quadratic function (0.233 x squared plus 1.685x plus 3.079. When we see the graph, those are the line and yeah, the parabola. Yeah, so those are the line and the parabola will go best fit the data is that parabola. Right, so that's pretty much it. Most importantly, if you ever turn on the stat plot or when we hit y equal 2 and you see this and you just want to graph it, you have to turn this off. Otherwise, they will have some weird behavior if this is on. So hit the second stat plot and turn off. When we're done with the plotting the point, we have to turn it off. So when we hit y equal 2, we don't see anything there. If it's highlight the plot, like I said, there will be some unexpected behavior. It will show some error when we graph it. So when we're done with the plotting the points, turn it off. Yeah. And once again, if we want to clear the list, hit edit, enter. Do not hit delete, just clear, enter, clear, and enter. Right? Yeah, if we want to name it, if it's blank like this, we can name it like second 3 for L3. Yeah, so we can name them if we accidentally delete it. Right, once again, if you want, and when we're done with stat plotting, yeah, when hit y equal 2, that should not be highlight any of them. And the windows, we actually change the windows. If we want to go back to the standard windows, hit zoom number 6. That gives us back to the standard windows. Right. So we cover polynomial. Once again, this is a review in cost algebra. And then we have something. This it might be handy in the statistic. Right. Just get familiar with the calculator. So I think that is necessary. Anyway, I will stop the video here. As always, thank you for watching and see you in another video in pre-calculus.